Ever wondered what happens when the load on a buck converter suddenly changes? Imagine your microcontroller switches from sleep to active mode, instantly drawing more current from the power supply. Let's simulate a few scenarios and see what happens. This is all my circuits. How does a buck converter respond when the load increases? Let's start with our simulation setup. We'll use a basic buck converter with a 24 volts input, an ideal switch, a PWM signal at 10 kHz, 50% duty cycle, and no feedback. A 1 mH inductor and 1 mF output capacitor. We'll also set the output voltage to 12 volts and the inductor current to 1.2 amps as the initial conditions to help the simulation quickly reach steady state. If you haven't seen the first video in this series, you'll find the link in the top right corner. To simulate a load change, we'll represent the load as a resistor. We'll begin with a 10 ohm resistor and switch to a 5 ohm load using an if statement. Keep in mind that the load increases when the output resistance decreases, because output power is proportional to the square of the output voltage and inversely proportional to the load resistance. We'll trigger the load change at 100 milliseconds, simulating a sudden increase, just like plugging in a new device. Now, let's run a transient simulation for 200 milliseconds and observe the output voltage and output current. When the load increases, the output voltage dips briefly, then recovers with some oscillations. We've seen in a previous video that the oscillations are due to the resonance of the LC circuit, and the output voltage finally recovers from the dip. To better understand where the voltage dip comes from, let's adjust the horizontal scale to between 90 and 110 milliseconds and plot the inductor and capacitor current. We see that at 100 milliseconds, the output current instantly doubles. Since the inductor resists a sudden change in current, the output capacitor temporarily supplies the excess current. This causes a dip in the output voltage while the inductor current ramps up to meet the new demand. Let's now explore how circuit parameters influence the undervoltage. First, we'll sweep capacitor values 0.5 millifarads, 1 millifarad, and 2 millifarads, and run the simulation. Let's zoom in between 90 and 150 milliseconds to better appreciate the effect of the output capacitor. As the capacitor value increases, the depth of the undervoltage dip decreases. However, the dynamic response slows down as the oscillation frequency is reduced. Next, we'll sweep the inductor values 0.5 millihenries, 1 millihenry, and 2 millihenries, reset the capacitor to 1 millifarad, and rerun the simulation. Let's adjust the time base between 90 and 150 milliseconds and add the inductor current plot. As the inductance increases, the undervoltage dip becomes more pronounced. This is because a higher inductance slows the rate at which current increases to recharge the output capacitor. Now that we've seen what happens when the load increases, let's find out what happens when the load drops. It should be straightforward, right? What happens when we reduce the load? We're still using the same buck converter configuration. Input voltage 24 volt, duty cycle 50%, inductor 1 millihenry, output capacitor 1 millifarad. This time we start with a load of 10 ohms, drawing 1.2 amps. Then, after 100 milliseconds, we reduce it to 20 ohms, cutting the current in half. We'll leave the simulation duration at 200 milliseconds and run it. Let's plot the output voltage, output current, inductor current, and capacitor current and adjust the time base to between 90 and 150 milliseconds. At 100 milliseconds, the load drops, and we see a voltage overshoot. This happens because the capacitor charges up from the excess inductor current. The inductor doesn't instantly recognize the load change and continues pushing current, but the lighter load can't absorb it all. The excess current charges the output capacitor, causing the voltage to rise. The increase in output voltage then forces the inductor current to reduce, and after a few oscillations, a steady state is reached. To ensure we fully understand what's happening, let's keep reducing the load even further. We can nest if statements to increase the load resistance in steps of 10 ohms every 100 milliseconds. Let's also increase the simulation time to 500 milliseconds and run it. We'll now plot the output voltage, inductor current, and output resistance. To plot the output resistance in LTspice, we can edit the output voltage trace and divide it by the output current. The output resistance plot shows clear increments of 10 ohms every 100 milliseconds. As we reduce the load, the converter initially behaves as expected. We do observe an overvoltage, but we understand its origin. What's concerning is that as the load resistance reaches 40 ohms and higher, the output voltage seems to drift out of control. Something unusual must be occurring. If we zoom in on the inductor current plot, we see that the current gets clipped to zero, and this somehow disrupts the converter. We have just discovered discontinuous conduction mode. What happens when the inductor current goes to zero? In continuous conduction mode, or CCM, the inductor current flows continuously throughout the switching cycle, even during the off time. We've seen this in our first video on the buck converter. But when the load gets light enough, the inductor current may hit zero and stay there until the next cycle begins. That's discontinuous conduction mode, or DCM. A third interval is introduced where the inductor is fully discharged and there's no current flowing in the power stage. It's not a fault, it's just a different operating mode, and it's quite common at low load. Let's set up the usual simulation in LTspice to analyze this mode in more detail. We'll use a 24-volt input, a 1 millifarad output capacitor, a 1 millihenry inductor, a PWM signal at 10 kHz with 50% duty cycle, an ideal switch without feedback. We'll simulate two resistive load values, 10 ohms and 100 ohms. We'll run a transient simulation for 200 milliseconds and plot the last millisecond. First, let's look at the main differences between CCM and DCM. We'll plot the inductor current, the switching point voltage M, and the output voltage. While the current in CCM is always greater than zero, in DCM the current reaches zero early and stays there until the next switching cycle. You can also see this on the switching node voltage. The waveform shows 3 distinct levels in DCM, instead of the usual 2 in CCM. If we check the voltage across the inductor, we notice something interesting. The intermediate voltage level appears in DCM. That's because when inductor current is zero, the voltage drop across the inductor is also zero. In contrast, in CCM, the inductor voltage is never zero during switching. Now, the important point. In DCM, the output voltage is not equal to the input voltage times the duty cycle. Instead, it follows a more complicated equation. If you're curious how that equation is derived, I've linked a great video in the top right corner. For our simulation values, the formula suggests a steady-state output voltage of 15.7 volts, and when we measure it in the simulation, we get a value that's extremely close. In conclusion, when the buck converter operates in DCM, the output voltage tends to spike, which is not desirable. There are ways to mitigate or avoid DCM, and we'll cover some of those in the next few videos. That's a wrap for today's video. The links to useful videos and simulation files are in the description. I hope you found this useful. Stick around for plenty more circuits to explore. This was All My Circuits.